Okay, let's unpack this. Imagine, if you will, a perfectly locked vault. We're talking about something mathematically impenetrable, right? A steel fortress where your most precious secrets, nestled deep inside, were absolutely safe. You'd think the combination, a complex string of numbers, was the only way in. But what if someone didn't need the combination at all? What if they could simply listen to the vault's intricate gears turning, feel the subtle vibrations as the tumblers fall into place, or even just sense the tiny electrical currents flowing through its mechanisms and from those seemingly invisible physical clues, reconstruct the entire combination? It sounds like something straight out of a high-tech spy movie, maybe.
Mm.
But this isn't fiction. This is precisely the sophisticated challenge facing our digital world today, especially with the cryptographic engines that silently protect everything from your online banking and personal data to the most critical national security infrastructure. Mathematically, these systems are often considered ironclad, based on complex algorithms designed to be practically unbreakable. But physically, the actual hardware that runs these algorithms can sometimes leak information like a sieve, inadvertently betraying the very secrets they're supposed to guard. Today, we're taking a deep dive into a fascinating and truly groundbreaking new research paper. It comes to us from a brilliant collaborative team at Purdue University, the Indian Institute of Science, and Intel Labs. The paper, titled Exploiting Clock Slew Dependent Variability in CMOS Digital Circuits Towards Power and EMSCA Resilience, might sound like, well, a mouthful of highly technical jargon, and it is, but trust us, the insights contained within are truly revolutionary, revealing a surprisingly elegant solution to a very pressing problem. Here's where it gets really interesting. Our mission today is to understand how these seemingly secure digital circuits can inadvertently betray their secrets through something called side channel attacks. We'll explore what these cunning attacks are, why many existing hardware defenses often fall short or are simply too costly, and how this clever, incredibly low overhead solution is now turning one of the chip's inherent weaknesses, the humble clock signal, into a powerful, unprecedented new shield. We're going to explore how a subtle manipulation of the clock slew, combined with intelligent randomization, offers not just an improvement, but a truly massive, almost exponential leap in hardware security. So, to start us off, what exactly are we up against here? When most of us think about digital security, we envision hackers trying to guess passwords, cracking complex algorithms, maybe finding software vulnerabilities. But side channel attacks operate on a completely different playing field. Can you describe, perhaps with a vivid image, what makes these attacks so insidious and hard to guard against?
That's a great way to put it. You're absolutely right. These aren't your typical digital hacking attempts. We're talking about side channel attacks, or SCAs. Instead of trying to break the code itself, they exploit the physical characteristics of a device during its operation. Think of it as forensic eavesdropping on the hardware itself. An attacker isn't trying to decrypt the message by brute force. They're listening to the hardware's operational whispers, gathering intelligence from its subtle physical behavior. For instance, we're talking about clues, like tiny fluctuations in power consumption as a chip calculates, the faint electromagnetic or EM emanations given off by its circuits, subtle timing variations in how long operations take, or even the patterns of how a processor accesses its memory cache, known as cache hits and misses. The crucial point here is that these are physical leaks. They allow an attacker to deduce secret information, such as a cryptographic key, without ever needing to crack the complex mathematics of the encryption algorithm itself. It's like determining the contents of a safe, not by knowing the combination, but by listening to the clicks as the dial is turned.
That's truly chilling. It feels like the mathematical perfection of our encryption is almost irrelevant if the physical implementation is leaky. How drastically can these side channel attacks reduce the effort needed to break what we consider robust encryption, and what are the real world implications of that?
Well, what's fascinating here is just how drastically these attacks can reduce the effort needed to break what we consider to be mathematically robust encryption.
Yeah.
For example, let's take AES 256, the advanced encryption standard with a 256-bit key. Mathematically, it's considered incredibly secure with a theoretical complexity of 2 to the power of 256, a number so astronomically large it's practically impossible to factor. But with a successful side-channel attack, that complexity can be reduced to something as low as 2 to the power of 13.
Wow. 2 to the 13.
Exactly.
Yeah.
To put that in perspective, 2256 is an unimaginable number, while 213 is just 8,192. That is a monumental difference, moving from impossible to frighteningly feasible for an attacker to break the encryption. And the paper provides a truly chilling detail. AES 256 keys can be intercepted from a meter away using a low-cost EM probe.
A meter away. Serious.
A meter away. Imagine a device protecting sensitive information, And an attacker can simply stand a few feet away with relatively inexpensive equipment and essentially steal the key.
Mm.
And here's the kicker. The attacker doesn't even need deep circuit knowledge or proprietary blueprints of the chip to achieve this. This isn't just a lab curiosity or a theoretical threat confined to academic papers. It's a significant, tangible danger to integrated circuits in everything from your smartphone to data centers, even from a distance, without physical contact. It literally changes the economics of attacking these systems, making what was impossible a very real threat.
So, how do they actually do this? How do attackers translate those faint whispers and tiny energy fluctuations into a secret key? Can you give us a simplified explanation of the core mechanics?
Absolutely. Let's briefly touch on the core mechanic of correlational power analysis, or CPA, and correlational EM attack, CEMA, as these are two of the most potent forms of SCA. In simple terms, attackers perform a sequence of steps. First, they collect traces, which are basically detailed recordings of power consumption or electromagnetic signatures from the cryptographic engine while it's in the process of encrypting data. They'll run the chip through many encryption operations, collecting thousands, sometimes millions, of these traces.
Okay, so they're just watching the device work, basically.
Exactly. Second, they know the ciphertext, the encrypted output, because that's usually public information. What they don't know is the secret key that transformed the original data into that ciphertext. Third, they essentially make educated guesses about what the chip's internal math should be doing for each potential piece of the secret key. They'll use predictive models, like the Hamming weight.
Hamming weight?
Yeah, Hamming weight just counts the number of 1 bits in a data word. Or Hamming distance, which counts the number of bits that flip from 0 to 1 or 1 to 0 during a transition. To understand this, imagine the chip's internal state. When it processes a new piece of data, its tiny transistors flip. An attacker isn't looking at the encrypted message itself. They're trying to figure out if, for instance, a lot of his zeros just became ones. That's a high Hamming distance because that transition draws a predictable amount of power. They use these models to guess what the chip should be doing internally for every single possible key byte.
So they're making assumptions about how the chip works physically.
Precisely. Finally, they correlate their hypotheses, their educated guesses based on these models, with the actual collected traces. They literally compare the predicted power signatures with the observed ones. Where the correlation is highest, and consistently so across many traces, the correct key byte is revealed. It's like finding the perfect match between a fingerprint and a suspect. The critical takeaway here is that these attacks are very generic. They require little knowledge of the architectures of the embedded crypto system being targeted.
Wow.
And that fundamentally is what makes them so incredibly dangerous and pervasive. Because an attacker doesn't need to be an expert in your specific chip design. They just need a general understanding of how crypto works and some basic equipment.
So if this threat of side channel attacks is so well known and has such a dramatic, chilling real-world impact, aren't there already solutions out there? Surely the industry isn't just sitting by.
Indeed, host, there are. The industry has been aware of SCAs for decades, and the paper categorizes existing countermeasures into 3 main types. But as we'll see, each of these approaches comes with its own set of significant challenges, often making them impractical, too costly, or simply not robust enough for widespread use, especially in resource-constrained devices like those found in the rapidly expanding Internet of Things, or IoT.
Okay. Let's delve into those traditional approaches then and understand their trade-offs. What's the first category?
The trade-offs are significant with traditional approaches. Let's look at the first category, architectural or masking countermeasures. These methods involve fundamentally modifying the algorithm or its implementation in software or hardware to obscure the data being processed. For instance, they might mask sensitive data by splitting it into multiple random shares that are then processed independently, only to be recombined at the very end. This means no single point in the circuit ever holds the complete secret.
Okay, that sounds pretty smart. Masking the data itself.
It is clever. They offer what's called provable security, which sounds incredibly appealing on paper because their security is based on mathematical proofs. However, they suffer from very high overhead, often requiring more than 100% additional circuitry.
Double the circuitry. Ouch!
Yeah, imagine a company designing a cutting-edge chip for, say, autonomous vehicles or critical medical devices. If a security measure demands double the circuitry, that's not just a cost issue. It might mean a chip that's physically too large to fit in a sensor, consumes too much power for battery-operated devices, or introduces unacceptable latency for real-time operations. It becomes a non-starter for many real-world applications. More critically, they are design-specific. This means if you change the architecture or algorithm even slightly, you often need a complete redesign of the countermeasure from the ground up.
That sounds like a nightmare for designers.
It really is. From an industry perspective, where design cycles are already long and incredibly expensive, this lack of flexibility is a major drawback. It severely limits their scalability and adaptability across different product lines or evolving standards.
So it's a powerful approach in theory, but the practical hurdles, the cost, the inflexibility make it difficult to implement widely. What about approaches that try to secure the power delivery itself? That sounds logical.
Exactly. The second category focuses on protection through the VDD, or power port. If we connect this to the bigger picture, this is a highly intuitive approach, right? If the power consumption leaks information, then logically, we should protect the power delivery network itself to minimize those fluctuations. These methods are generally generic, meaning they can be applied to various cryptographic algorithms and have low area overhead, which is a plus for keeping chip size down.
Okay, sounds better so far. Low area overhead is good.
But, and this is a significant but, they frequently introduce high droop.
Hi, Drew. What's that?
It refers to undesirable voltage fluctuations in the power supply. To counteract these fluctuations and stabilize the power, you often end up consuming significantly more power. This leads to high power overhead, which is detrimental for battery-powered devices.
Ah, so you fix the leak but drain the battery faster?
Pretty much. What's even more problematic is that many of these solutions involve large passive components, such as metal insulator metal or MIM capacitors, used to smooth out voltage spikes. Ironically, these very components can themselves emit important information through electromagnetic emanations, effectively creating new side channels that attackers can exploit.
Wait, so the fix creates a new way to leak.
Sometimes, yes. So while you're trying to solve one problem, you might inadvertently be creating another, or even multiple new ones. Techniques like integrated buck regulators or IBRs fall into this category, but as mentioned, their passive components can become a liability. Digital low dropout regulators, or digital LDOs, are another approach often used to deliver stable power. However, they are inherently susceptible to leakage because their voltage compensation mechanism closely mirrors the chip's instantaneous current draw.
Which is exactly what the attackers are looking for.
Precisely. Some of these promise great security, but they are not synthesis-friendly.
Meaning hard to build.
Hard to integrate into standard chip design flows that rely on automated tools and predefined building blocks. This makes them difficult to manufacture economically and at scale, severely limiting their real-world impact.
It sounds like a constant game of whack-a-mole, where every solution seems to introduce a new vulnerability or a prohibitive cost. Given that the idea of using the clock signal for protection has come up before, hasn't it? What's the third category?
It has. And that brings us to the third category, protection through the clock port. This is where our deep dive gets particularly relevant. Some existing techniques have attempted to randomize the clock signal, but primarily at a system level. For example, they might randomly shift the clock frequency slightly, or introduce jitter to disrupt the attacker's ability to align power traces over time.
Okay, messing with the timing. Seems plausible. Did it work?
Well, the problem. These approaches have unfortunately been rendered ineffective by clever post-processing techniques. Attackers are sophisticated. They can use advanced mathematical methods like trace alignment, sometimes even employing powerful machine learning algorithms like convolutional neural networks or CNNs to undo the randomization.
Wow, using AI to defeat the randomization.
Exactly. It's like having a blurry photo and using advanced software to sharpen it and bring the hidden details back into focus. They can also use FFT-based frequency domain attacks to still find the underlying leakage, even if the signal is randomized in the time domain.
FFT, fast Fourier transform, so looking at frequencies instead of time.
Right. By converting the signals to the frequency domain, they can often filter out the randomization and pinpoint the frequencies where sensitive information is still leaking. This raises an important question. If system-level clock randomization fails, what about changes at a much more fundamental circuit level? This area, remarkably, has been relatively unexplored until now, representing a significant gap in our hardware security toolkit.
It sounds like we've been trying to solve a puzzle, but every time we get close, the pieces change, or the puzzle itself becomes fundamentally harder due to clever attackers. Given that rather sobering landscape of existing defenses, solutions that either cost too much, are too inflexible, or simply can't outsmart the latest attacks, it's clear the industry needs a genuine paradigm shift. And that's exactly what this research delivers by turning our attention to the very heart of digital timing, the clock signal itself.
All right, now that we've set the stage, let's really dig into the mechanics of this groundbreaking approach. How does it propose to use the clock to create a more robust shield? Indeed, the industry is craving generic circuit-level countermeasures that are both low-cost and genuinely effective. And this paper steps in with something truly innovative. The core concept is to exploit what they call the inherent variability of CMOS digital circuits using a controlled slewed clock. It's about taking something that was often viewed as a signal integrity challenge, the non-ideal nature of a clock signal, and transforming it into a powerful new strength for security.
Okay, controlled slewed clock. Let's break that down. What exactly is slew?
Right, so let's start by defining slew in this context. In simple terms, slew is the rate of change of a voltage over time, often expressed as dVdt. Think of it as how quickly an electrical signal transitions from a low voltage to a high voltage, or from high back to low. Imagine a light switch. An ideal clock signal is like flipping that switch instantly. The light goes from off to on with zero delay. We'd say it has an infinitely sharp instantaneous transition, or infinite slew rate. A slewed clock, on the other hand, has a slower, more gradual transition. It's like using a dimmer switch to slowly fade the light up or down. That gradual slope is the slew.
Okay, so instead of a sharp on-off pulse, it's more of a ramp up and ramp down. How does that help security?
Well, the breakthrough here is how this controlled slew transforms the power and EM emanations coming from the chip. Instead of the leakage being a simple direct function of the secret data being processed, a clear signal an attacker can easily model, it becomes a complex function of data in slew. This means the side channel information is no longer just about the secret data. It's now tangled up, intertwined with the clock's unique, subtle characteristics. This complexity makes it exponentially harder for an attacker to disentangle the secret data from the deliberate noise introduced by the clock's slew. Their models, which rely on predictable power spikes, are fundamentally broken.
So you're confusing the attacker's models by tying the leakage to the clock's behavior, too.
Precisely. Crucially, introducing slew also reduces the leaky frequency. This means the specific frequencies at which sensitive information might typically leak become less distinct, or their energy is spread out over a wider range, or even shifts unpredictably. This makes frequency domain attacks, which rely on identifying those precise, consistent frequencies, significantly harder to execute successfully. It's like trying to find a specific radio station when the broadcast signal itself is constantly shifting its frequency.
Okay, that makes sense. And you mentioned combining this with randomization.
Yes, and here's the real kicker, the truly remarkable part. When you combine this intelligent clock slewing with clock randomization, the effects aren't just additive, they're cumulative. This creates a security boost far beyond what each technique could achieve alone. Imagine you have two security measures, one that makes something 100 times harder, and another that makes it 5 times harder.
You'd expect maybe 105x or 500x improvement if they multiply.
Right, but the paper reports an 1800x improvement in minimum traces to disclosure, or MTD, when both are combined.
Whoa, 1800 times.
Yeah. This cumulative effect is a critical discovery because it means these two defenses work synergistically, making each other exponentially stronger. What's more, this is a generic synthesizable countermeasure technique, meaning it's easy to implement using standard chip design tools and processes, and it can work with many different cryptographic designs. And perhaps most importantly for practical adoption, it has extremely low overhead in terms of additional circuit area, power consumption, and performance impact.
That's truly remarkable then. It's not just about slowing down a signal. The brilliance here is how this seemingly subtle change triggers a cascade of effects within the chip, essentially creating a chaotic environment for any attacker trying to pinpoint data leakage. It's like adding tiny, unpredictable ripples to a pond where an attacker is trying to spot a specific fish. Rather than just masking the information, the slew is fundamentally distorting the very physical signals an attacker relies on. Let's break down these artifacts, or internal effects, the paper identified. These are the underlying mechanisms by which the slewed clock actively disrupts side-channel attacks at their source.
Absolutely. What's fascinating here is how deeply the clock slew interacts with the fundamental physics of digital circuits, right down to the transistor level. It's not just a superficial change. It impacts how the very building blocks of the chip behave. First, let's talk about register internal clock slew. When a slewed clock signal arrives at a flip-flop, which is the basic memory unit in any digital circuit, storing a single bit of information, that slew doesn't just disappear. It actually propagates through the internal buffers and gates of that flip-flop.
So the slowness travels inside the memory cell.
Exactly. Imagine a 0 to 1 transition for a single bit. With an ideal sharp clock, the transistors inside the flip-flop switch very quickly, drawing current in a predictable sharp burst. But with a slewed clock, those transistors transition more slowly, taking a little longer to fully turn on or off.
Yeah.
This changes how current is drawn, and crucially, for how long it's drawn, stretching out the energy signature. The key insight here is that different parts of the flip-flop, say, the internal latches responsible for storing a 0-1 versus those for storing a 1-so-1, might experience slightly different effective slews due to minute design variations. This causes subtle, data-dependent timing shifts in their operation. The result is an extra variance in power traces that isn't purely due to the data being processed. It's a subtle but powerful obfuscation, like a musician playing a note, but the exact timing of the note is slightly unpredictably off based on the instrument's internal mechanics, making it harder to track in a melody.
Okay, so internal timing gets jumbled. What's next?
Second, we have uneven duty cycle distortion. An ideal clock is typically designed to be high for exactly half its cycle and low for the other half. That's a perfect 50% duty cycle. A slewed clock, however, particularly when it interacts with internal circuit variations, can lead to non-ideal or uneven duty cycles. This means the clock might be high for, say, 48% of the time and low for 52%, or vice versa, and this can vary across the chip.
So the clock isn't perfectly balanced anymore. What does that do?
So what does this all mean? This distortion changes the precise timing of various power and EM leakage points within the power supply network. Instead of all the tiny power leaks from different flip-flops and gates accumulating neatly and predictably at one specific moment in time, creating a sharp, easily detectable spike for an attacker, they get distributed over a large number of time samples. This smearing effect makes it harder to exploit by an attacker who is trying to find a clear, sharp, and consistent signal of secret data. It's like trying to find a single distinct note in a heavily reverberating echo chamber where all the sounds are blended and delayed.
Smearing the signal out over time. Clever. What's the third effect?
Third is slew-dependent latch delay. Side-channel attacks, especially those based on the Hamming distance model, heavily rely on detecting transitions in the state registers, like a bit flipping from 0 to 1 or 1 to 0. An attacker knows that a transition from 0 to 1 often draws a different amount of power than 1 to 0. With an ideal clock, the latching times, which is when data is captured by a flip-flop, mainly depend on the data itself and its transitions, leading to predictable power signatures. But with slew introduced, the latching time becomes a function of data and slew.
Ah, so when the data gets saved depends on both the data and the slow clock.
Exactly. Different slews reaching different internal clock nodes within the flip-flop mean that latching a 1 might take a slightly different amount of time than latching a 0, or even just processing a 0 versus a 1 can be subtly affected. This again introduces more extra variance into the power traces, making it significantly more difficult for an attacker to correlate a predictable power signature directly to the secret data. The attacker's model of expected leakage is fundamentally broken because the timing is no longer solely data-dependent. It's now a complex interaction with the clock's slew.
Okay, that's 3 ways the slew messes things up internally. You mentioned post-fabrication effects too, things that happen after the chip is made.
Right, and finally we have 2 post-fabrication artifacts: amplified Elmore delay variability and intra-die variation. These effects kick in even after the chip is built and the silicon is set, and the slewed clock continues to work in our favor. The Elmore delay refers to how electrical signals propagating through long wires on a chip get distorted and delayed due to the wire's inherent resistance and capacitance.
Right, like signal degradation over long distances on the chip.
Exactly. If I'm picturing this correctly, it's like shouting a message across a really long, twisty corridor. By the time it reaches the other end, it's not as clear or sharp as when you started. The signal gets muffled and delayed by the resistance of the hallway itself. When a signal is already slewed, this Elmore effect further distorts it in a nonlinear way, significantly amplifying the variability of the signal as it travels across the chip. This added, unpredictable distortion is exactly what you want to foil an attacker. And this is further aided by intra-die variation. These are tiny, unavoidable, microscopic differences that occur during the manufacturing process across a single chip. No 2 transistors or wires are ever perfectly identical, even side by side.
The tiny flaws inherent in manufacturing.
Correct. The slewed clock magnifies the impact of these minute, inherent manufacturing variations. Because the signal isn't sharp and ideal, these tiny imperfections have a much larger, more unpredictable effect on signal propagation and timing, further enhancing the unpredictability of leakage and bolstering resilience against attacks. It's truly a multi-layered defense that cleverly utilizes the fundamental physics and unavoidable imperfections of the chip itself to create a shield.
So we have this elegant clock slewing technique that cleverly messes with the internal timing and spreads out leakage, making it incredibly difficult for attackers to get a clear, consistent signal. That's a powerful defense on its own. But the paper doesn't stop there. The real power, the truly revolutionary aspect, comes from combining this with intelligent clock randomization. Here's where it gets even more interesting, because the two techniques together create a defense that is truly more than the sum of its parts. It's a synergistic effect that amplifies security to unprecedented levels.
Exactly. It's a highly effective one-two punch against attackers. Let's first quickly re-explain how the clock randomization works in this system, as it's designed to be more robust than previous system-level approaches. The architecture employs a frequency generator that randomly selects clock frequencies. This involves a tunable ring oscillator, or RO, which can be configured for fine-tuning frequencies.
A ring oscillator, basically a loop of components that naturally oscillates.
Yes, and it's tunable. The paper describes 8 different configurations, allowing for a range between 49 and 81 stages, which a multiplexer can randomly select. For coarse randomization, a 3-stage toggle FF-based divider is used. An LFSR, or linear feedback shift register, is seeded by a true random number generator, or TRNG, ensuring these changes in clock frequency are genuinely unpredictable and not easily reverse engineered.
TRNG, so real randomness, not pseudo-random.
Correct. The key is that the clock frequency itself is constantly unpredictably changing. Now, for the synergistic effect, this is crucial. Recall that system-level clock randomization on its own was often easily defeated by frequency domain attacks and sophisticated post-processing techniques.
Right, the attackers could just clean up the signal.
Exactly. Attackers could simply align the traces or use filters to strip away the randomization, making the signal clear again. However, with the slewed clock already in place, the clock randomization countermeasure is more effective as it becomes more difficult to post-process in the frequency domain. The slewed clock fundamentally alters the nature of the leakage itself before the randomization even kicks in. It reduces those leaky frequencies and makes the leakage patterns less distinct, less sharp, and harder to categorize. So when you then apply randomization on top of that, even if attackers try to align traces or filter specific frequencies, the randomized slewed clock has already hidden the information so effectively that those post-processing techniques lose their bite.
Ah, so the signal is already muddied by the slew before it's randomized, making it much harder to clean up later.
Precisely. The attacker's ability to clean up the signal is severely hampered. It's like trying to untangle a knot that's already been deliberately frayed and confused.
So the slewed clock isn't just adding noise, it's fundamentally changing the character of the signal, making the subsequent randomization exponentially more potent. That's a truly clever design. What do the results look like when these two forces combine? How much more secure are these chips? You mentioned MTD earlier.
Yes, the jaw-dropping results in terms of minimum traces to disclosure, or MTD, truly quantify this enhanced security. MTD is the metric that tells us how many power or EM traces an attacker needs to collect to reliably reveal the secret key. The lower the MTD, the easier it is to break. So let's look at the numbers. For an unprotected AES implementation, the key was revealed with a mere 11,000 traces using a power analysis attack.
11,000, that sounds worryingly low.
It is. To put that in perspective, a determined attacker with readily available equipment could gather that many traces in minutes, or at most a few hours. That's incredibly vulnerable, showing just how quickly a key can be compromised. Now, slewed clock AES, SLAES, alone improves security by a factor of 100 times, requiring 1.2 million traces.
Okay, 100x better. That's significant.
It is. This is a significant improvement, pushing the attack window from minutes to days or even weeks. And importantly, frequency domain attacks failed completely against this. The slew effectively rendered them useless, demonstrating its power against a common attack vector. Then, clock randomized AES, CRAAES, alone offered a 5 times improvement over the unprotected version, needing 70,000 traces for a successful attack.
But
Yes, this was only after attackers used post-process techniques like bandpass filtering to clean up the signal. Without that specific post-processing, it still took over 270,000 traces to extract a key in the frequency domain. This shows that randomization alone is effective, but vulnerable to advanced signal processing. Now, for the combined force, what they call CRSL-AES, this is the game changer. For traditional power analysis, CPA, the correct key was not revealed even after collecting over 20 million traces.
20 million and still no key.
Still no key revealed. That is an 1800x improvement over the unprotected version. Think about what that means. An attacker would need to collect an unimaginable amount of data, requiring weeks or months of continuous operation, potentially encountering device resets or power cycles, making a successful attack practically impossible with today's technology and resources. The correlation peak never emerged above random noise, meaning the secret key remained indistinguishable from pure randomness. For leakage analysis using TVLA, or test vector leakage analysis, which is a statistical test for any observable leakage, it showed a staggering 40,000x improvement over unprotected, with no detectable leakage until 6 million traces.
40,000 times better. That's astronomical.
It really is. To put that in perspective, an unprotected system started leaking with just 110 traces in TVLA. That's truly remarkable, indicating a profound and robust increase in resistance. And the results were equally impressive against EM attack resilience, CIMA. The unprotected AES was broken with just 6,500 traces, but the combined CRSL AES was resistant to CIMA even after over 20 million traces. Both time domain and frequency domain EM attacks failed.
So it works against power and EM leakage.
Exactly. This means the defense is effective across different types of side channels, not just power. So what does this all mean? The paper unequivocally shows that the cumulative effect of combining Slew and randomization is more than the multiplicative effect of the individual techniques.
It's not just 100 times 5, it's 1800x or more.
Precisely. It's a profound exponential interaction. It's like having two sophisticated locks on a door. But the presence of each lock makes the other exponentially stronger and more complex to pick. This dramatically raises the bar for any attacker, moving a feasible attack into the realm of the practically impossible.
That's incredibly impressive from a security standpoint. These numbers are truly mind-boggling. But often with security, there's a huge trade-off. You might get more security, but your device becomes slower, physically larger, or consumes too much power, making it impractical for many real-world applications, especially in areas like IoT or edge computing where resources are tight. This is where this research truly shines because it delivers these massive security gains with remarkably low overheads, making it a viable and attractive solution for widespread adoption.
Indeed. The numbers speak for themselves regarding practicality. This solution achieves low overhead with high impact, which is the holy grail in hardware security. Let's start with area overhead. It's a mere 11%.
Only 11%. That seems tiny for this level of security.
It is. This is one of the lowest compared to existing state-of-the-art countermeasures. For anyone in chip design, an 11% increase in chip area is remarkably low. To give context, even a few percentage points of area can significantly impact manufacturing costs and the physical footprint of a device. Keeping it this low means it can be integrated into tiny IoT sensors or resource-constrained edge devices without significantly altering their form factor or price point. The clock generation circuit itself is remarkably tiny, using minimum-sized inverters and a multiplexer. The main area increase comes from small load capacitors, but even then, the total is less than 8 picofarads, which is truly minimal in the grand scheme of chip design.
Okay, area is minimal. What about power? That's critical for mobile and IoT.
Right. Next, power overhead. This is less than 3% as measured, and it's the lowest reported amongst the countermeasures to date.
Under 3% power increase? That's amazing. Why is there any increase at all?
Good question. This raises an important point. Why is there any power overhead at all if we're just manipulating a signal? It's primarily due to what's called short-circuit power. When the clock signal transitions slowly due to Slew, there's a brief period where both the PMOS and NMOS transistors in an inverter can be on simultaneously. This creates a direct current path from the power supply, VDD, to ground. While this current flow increases with Slew, the paper demonstrates that this increase is very small compared to the power drawn during the normal, active operation of the AES engine itself.
So it's a tiny side effect of the slow transition.
Exactly. For battery-powered devices, where every milliwatt counts, a 3% overhead is a perfectly acceptable trade-off for such a dramatic security boost.
And performance. Does slowing the clock edge slow down the whole chip?
Finally, performance overhead. This is also impressively low, less than 6% as measured. There's an important trade-off here to understand. While adding Slew improves security, if you add too much Slew, for instance, by loading the clock port with a very large capacitor, say greater than 1 picofarad, the clock signal might not reach the toggling point quickly enough for the flip-flops to operate at higher frequencies.
Ah, so too much Slew could break things or force you to run slower.
Correct. This could cause functional failure, meaning the chip simply stops working correctly, or at best, it would significantly reduce the maximum operating frequency of the entire chip, slowing it down. The research team carefully chose an optimal operating point, using a maximum of 870 femtofarads of load capacitance to ensure minimum performance drawback while maximizing security. This is a critical design consideration that balances achieving robust security with maintaining practical usability for real-world products.
So they found the sweet spot, low overheads all around. What about actually implementing this? Is it easy for chip designers?
That's another significant advantage. The solution is synthesizable and generic. It is fully synthesizable, meaning it uses standard cells and standard automated design tools without requiring any custom, difficult-to-manufacture modifications.
So it fits right into how chips are normally designed today?
Exactly. This makes it incredibly easy and cost-effective to integrate into existing industry design flows, shortening development cycles, and reducing manufacturing complexities. It's also generic, meaning it can be easily combined with any of the VDD countermeasures to enhance SCA resilience.
Like those power port defenses we talked about earlier?
Yes, this modularity is a huge advantage, allowing designers to layer multiple defenses for even greater security without needing complete redesigns, giving them flexibility in securing various applications. And this isn't just theoretical research confined to simulations. The researchers fabricated and tested their solution on an actual integrated circuit built with TSMC 65mm CMOS technology.
They actually built it and proved it works in silicon.
They did. They thoroughly demonstrated its efficacy in real silicon, showing that their findings and impressive security gains hold up outside of controlled simulation environments. This kind of real-world validation is incredibly important for fostering industry adoption and proving the viability of the technique.
So what does this all mean for you, our curious listener? This deep dive has shown us how a seemingly small, almost invisible physical property, the way a clock signal transitions, that subtle slew, can be leveraged to build a truly formidable defense against sophisticated side-channel attacks. It's a powerful testament to the ingenuity and hardware security, proving that mathematical perfection in cryptography isn't enough on its own. We absolutely need physical resilience built into our circuits too. This low overhead, synthesizable, and generic countermeasure, particularly when combining clock slew with intelligent randomization, offers unprecedented protection for our digital devices without bogging them down in terms of size, power, or speed.
Yeah, and if we connect this to the bigger picture, this research truly opens up an exciting new area in hardware security. It fundamentally demonstrates that the clock port, which has often been overlooked in circuit-level security countermeasures in favor of power or architectural modifications, can actually be a primary defense mechanism. And, as the paper highlights, combining it with existing power port solutions offers a multiplicative effect on security, essentially creating a multi-layered defense that is greater than the sum of its parts.
That layered approach sounds critical.
It is. This is incredibly crucial for edge devices and the rapidly growing Internet of Things, or IoT, ecosystem. In these environments, resources are often severely limited. Small batteries, tiny processing power, minimal memory. But the need for robust security is absolutely paramount, especially as these devices become ubiquitous and handle sensitive data. This approach provides a viable pathway to strong, practical security, even in those most constrained settings.
We've seen how a subtle, almost imperceptible change to the clock's slew can turn a cryptographic engine from a leaky vault into an almost impenetrable fortress against physical attacks. It makes you wonder, doesn't it? What other invisible physical properties of our everyday devices, from our smartwatches to the chips in our cars, might be hiding both vulnerabilities and equally elegant, low-cost solutions, just waiting for someone to deep dive and discover them? The physical world around our digital bits and bytes is clearly still full of secrets, waiting to be unlocked for security. Keep exploring, keep questioning, and join us next time on The Deep Dive.